So now let's talk about the shear center. The shear center, if I translate into 우리말, this is called 전단 중심. So although the concept of shear center, the definition of shear center is given in the textbook. So I think the subject of shear center is not. It doesn't produce the correct concept to this subject. So rather than that, I'd like to call it not to any point, the loading point, not to cause any twisting action in beam cross sections. This is the subject for the shear center. Okay, so if I explain you the concept of shear center in an easy way, the key point is where we apply the load, not to cause any twisting deformation in the beam cross section. So make sure that the discussion that we made up to this point in the chapter of beam problems, so everything we discussed, most of the information that we discussed, on the assumption of a two-dimensional bending plane. So we discussed the beam problems in two-dimensional space. We never considered any three-dimensional effect in these beam problems. So here, let's consider cantilever. In this cantilever, I have the loading, external loading here, and then I have this support. Then, because of force equilibrium, I can calculate the reaction here. The reaction moment is equal to P times the length of the beam. Then I can obtain the shear force diagram and the bending moment diagram. Then I have the normal stress using the beam formula. By the way, I forgot the minus sign here. And then I can calculate the shear stress. Tau is given by the shear force times the first moment of cross section divided by second moment of inertia and then the thickness of beam. The problem is this is the two-dimensional problem. So let's consider what happened in real situation. In real situation is this is the three-dimensional view of this beam problem. So in real situations, I have another axis, z-axis here. So in this two-dimensional analysis, we do not have z-axis here. So let's imagine where we apply the load. So we can apply the load here and the B, and then we can apply the load some other point, okay, rather than just on top of the beam cross section. So we are gonna apply load here, E here, with the eccentricity E. Then what happened here? In this three-dimensional configuration, although we have difference in the loading points, but in this two-dimensional analysis, there's no way to distinguish the difference in the loading points. We have the same loading point here in two-dimensional space. But we calculate the shear stress because there's no difference. We calculate the shear stress using this loading only. So it doesn't matter where you apply load here and here, but we have same shear stress distribution, isn't it right? But the consequence is very significant. Let's imagine a rectangular section. As I told you, we have the same shear stress distribution because we use the beam theory. Okay, for load A and load B. Let's consider load B. In the case of load B, we apply load here. This is load B, okay? So the twisting moment produced by external load P is equal to 0 if you calculate the torsional moment with respect to loading point. And how about twisting moment, the shear stress produced by this distribution of torsional moment produced by the shear stress with respect to this loading point? Because the shear stress distribution is symmetric with respect to this point, it is equal to 0. So in that case, we do not have any non-zero twisting moment. But if you apply load here, like A, so if you apply load here, P, if you apply load here, as given in A here, P. And then let's try to calculate twisting moment. Twisting moment caused by load P is P times 0 is equal to 0, isn't it right? But how about twisting moment produced by the shear stress? So we have certain the resultant of the shear stress. We have this force, isn't it right? Certain kind of force caused by the shear stress. And then do we have arm length? Yes, we have arm length here, non-zero arm length, some distance r. This is not obviously not equal to 0. So which means we have non-zero torsional moment. Because of this non-zero torsional moment, so we must have twisting action in this beam cross section. This is the key point to understand the concept of shear center, okay? So, summarize. So we calculate the shear stress distribution in the beam theory. The problem is in real situation is not in two-dimensional configuration. So we need to find a loading point so where there is no twisting action. This is the key point. So this is a real situation. If you imagine a twisting section, the channel section, if you apply load to an arbitrary point, because of the mismatch in the torsional moment produced by the external load and the torsional moment produced by the shear stress distribution here, and it causes twisting action. And then to discuss the shear center, first we have to calculate the shear stress distribution. So tau is equal to shear force Q and I and B. And instead of dealing with the shear stress, actually dealing with shear stress is okay. But in most cases we use thin, thin sections instead of using the shear stress. It's better to use shear flow. Let's move the thickness into this direction, Then we have the shear flow. The definition of shear flow is the shear force per unit distance. This is the shear flow. This is easy to calculate the torsional moment produced by the shear stress. Okay, so instead of talking about detailed calculations, I'd like to discuss the problem intuitively. Let's say we apply loading here to any point on web section. So I have loading here, P. So I want to calculate the torsional moment with respect to this loading point here. And obviously, the arm length to the loading point is equal, the load itself is equal to 0. The torsional moment caused by the loading is equal to 0. Then how about the torsional moment produced by the shear flow? So here in the case of I-shaped section, the distribution of the shear flow is symmetric. But because of this symmetric property, it is equal to 0. So which means if you apply load on the line of this symmetry here, then it doesn't cause any twisting action. But how about channel section? So let's say we apply load, for example, where we want to apply load. So let's say we want to apply load here. Okay, let's say we want to apply load here, P. So as I told you, let's try to calculate the torsional moment. The consequence of torsional moment is what? Torsional moment produced by the external load. As I told you, the arm length is equal to 0. This is equal to 0 here. Now let's try to calculate torsional moment produced by the shear flow. Look at this. The distribution of shear flow is counterclockwise. So obviously this is not equal to 0. It produces, non-zero torsional moment in the counterclockwise direction. So if you apply loading to this point, it produces, non-zero torsional moment in this cross section. Because of this, it produces torsional, twisting action. So it violates the assumption of beam problem, isn't it? That's why we shouldn't apply load here to satisfy the assumption of beam problem. So where we apply the load. So it is true that this guy produced what, non-zero torsional moment if you calculate torsional moment with respect to this point. So let's try to move our the loading point here. So if you apply loading point here, loading point here, then again the torsional moment produced by loading is equal to 0. Now the situation is a little bit different. So the top and bottom flanges produce what? The torsional moment in clockwise here now. Okay? But the shear flow in the web produce, this is clockwise, sorry. These top and shear flow and top and bottom flanges produce counterclockwise torsional moment. But the shear flow in the web produce clockwise torsional moment. So if you adjust the point carefully, so we can find some point where the torsional moment produced by the shear flow is equal to 0. So we have to find that point, okay? We have to find that point. This is how we determine the shear or the center. Now how about the angle section? In the case of angle section, maybe the distribution of shear flow look like this, isn't it right? Then where we have to apply load. So we need to find a point, the torsional moment produced by the shear flow is equal to 0. So we can make that torsional moment is equal to 0, letting the arm length is equal to 0, which means we have to apply loading here, okay? Isn't it? So if you apply loading here, then it doesn't cause any twisting in this cross section. Usually, if you have an intersecting point, then we should apply loading to here. The angle section, we have the load applied here, in that it doesn't cause any torsional moment. And also V section, and then cross section too. Okay. And then in the case of Z section, this is an anti-symmetric section, so we have to apply loading to the anti-symmetric point, not to cause any twisting section. So here, let me take 10 minutes break before we discuss elastoplasticity.